What is persistence? It is a set of techniques allowing to persist in the target environment. In other words, these are all technical and operational means of preserving access to your victim organization, including the ability to survive a machine reboot. Now, why bother? Why is it important? So the first answer is pretty obvious. After you successfully breached into your target, either through spear phishing or by exploiting some vulnerability and crossing the perimeter, you land in an environment about which you probably don't know too much. So you need time to make a proper recon before you move further with your post-exploitation activities, right? So that's one. You're buying some time for your team to be able to accomplish your objective. And that brings me to the second point, operational security. Obviously, you operate within certain constraints, either time constraints, scope constraints, or any other you defined at the beginning with your customer. But that doesn't mean that once you land on a box, you start scanning internal networks like crazy, okay? First of all, real threat actors don't do such things. So if you want to simulate or emulate adversary realistically, you should start low and slow and move further without making too much noise. It all costs, time and effort and good understanding of your craft. And that's where a good, well-hidden persistence can save you from a lot of trouble. But it's also a double-edged sword. If you use well-known, well-understood, and easily discoverable persistence method, your operation can get burned very quickly, okay? So number 2 is OPSEC. Now imagine that you're on an engagement which lasts 6 months. And I know that this doesn't happen too often to have that kind of comfort, but just for a moment, think about such an operation. You have 6 months to get a list of objectives you received from your customer, okay? And your goal is to accomplish them without being detected. So how on earth would it be possible if you don't employ several not well-known persistence methods? And why am I talking about it? Because I want you to start thinking about your behavior during your engagements. Does it really look like a real adversary emulation or simulation? And how do you measure that? The whole sektor7 project is about teaching you not only technical skills, but also how to operate the right way, stay invisible, think about your tradecraft and your tools, your footprints you leave behind, your OPSEC, your understanding of TTPs, and how to preserve an edge over the defenders, okay? These are all the things we teach in sektor7. And persistence is just one of those. So what are we going to cover? I will tell you about some well-known persistence techniques like run keys, startup folder, Logon Scripts, Screensavers, and profiles. Then we will walk through DLL hijacking and DLL proxying, which is just a DLL hijacking with preserving hijacked functionality, okay? The same goes with comms, component object model. So how to hijack and build a com proxy. Then we will move to methods which require local admin privileges, including multi-action tasks, app shims, image file execution options, WMI Event Subscriptions, AppCert DLLs, AppInit DLLs, Winlogon, time providers, and port monitors. Finally, I will show you how local security authority, also known as LSA-as process, can be used for persistence. And at this point, you will learn 3 different techniques of surviving a machine reboot within LSA-as. Before we jump into the course, I need to give you some additional information. So all techniques are grouped into separate subgroups. One will cover persistence methods that do not require local admin privileges, and the second will cover the rest. In your course materials, you will find C code templates with a text file containing all commands used during the course. So you don't have to worry about the syntax, okay? Third thing you have to be aware of is that some techniques will run your payload multiple times, meaning that if you want to use them operationally, you will have to implement some additional control mechanism for spreading using stuff like mutexes, files, events, or something similar. So code course doesn't have that, but it's pretty easy to implement such control using Windows API. And speaking of payload, for the exercises, I'll be using standard simple shellcode which spawns a notepad process, but with provided code templates, it will be super easy for you to reshape the code and use something more realistic. For example, Meterpreter, Empire Beacon, or any other payload you commonly use during the operations. And at the end of this video, I'll show you the implant code used in the course. The next thing, after every shown technique, I'll be doing a cleanup so we don't end up with several implants popping up simultaneously, okay? And I encourage you to do the same. And the last but not least, each technique will be preceded by an intro slide describing the name, the required access level, and which thread group or malware used this particular technique. Okay, let's take a look at an example. So used by section will contain threat actor names like APT28, Cozy Duke, etc. Everyone means that the particular technique is very popular, okay? And unknown means that the technique is either not known or I haven't found too much information about the threat actors who use it. And here's an example. So the name of the technique is Local Security Authority, which needs local admin privileges, okay? And was used by Flame malware in a particular technique using authentication packages. Equation group used that in Dark Pulsar by implementing a security support provider, okay? And Project Sauron used password filter for that technique. So let's take a quick look at the implant code used in the course. So in your course material, you can find an implant folder, okay? And it holds several files, implant.cpp, implant.dll.cpp, and implant.srv.cpp. So these three files contain a C code, which will generate, the first one generate the standalone exe file, DLL will generate a DLL, and this is going to generate a Windows service. Okay, so let's take a look at the source code of implant.cpp. And those of you who took other Red Team Operator courses like malware development or local privilege escalation should be familiar with that code because it's pretty much the same. So what we have here, we have a simple main function which will start our payload either from the which is encrypted by the additional Python script, or we just start Notepad, like creating a new process, calling Notepad. But if you need to weaponize that script, you can use that comment out code, which will take your payload and decrypt them and just run it in a separate thread here. So we resolve two functions, virtual alloc and RTL move memory. Then we we allocate new memory. We decrypt our payload, and we copy that payload into allocated memory, okay, and then we change protection settings on that allocated memory to execute and read. And if all is successful, then we create a new thread calling that payload, decrypted payload. So where is the payload? Payload is here. So it's a long string, okay, byte string, and a key is here. And AES decrypt function is defined here. So we use Crypt API, Windows API to decrypt the payload. And if you want to encrypt your payload, so the payload we are using in here is actually this one, which spawns a new thread. Excuse me, it spawns a new process, in our case a notepad. And but you can use that using this AES Py script, and use it is really simple. So you call Python AES and the name of your payload, which has to be in binary form. So if you use Meterpreter, for example, you have to generate the Meterpreter in a raw format and save it in a file, and use that as a parameter for the script. And when you run it, you get two variables, two results. So this is your key. So you take that and you just copy that here into this key line. And the same goes with the payload. So you just take that part and copy this into this line. And you save that and you should be good. So that's the payload we are going to use during the course. After downloading our OVA file, it has to be imported into our VirtualBox. So we click import, then we select a path to OVA file, click next, then choose your machine base folder here, click import, and the machine is being imported. We will get back to the video after it has completed. And now, once the machine is imported, we can start it up. Please take a note the credentials to access your machine. So user is RTO, password is passw0rdbank. Okay, so let's start. So now we can log in. So Course VM is based on Windows 10 Enterprise Evaluation, available from Microsoft website. So the last thing we need to do is to extract our course material into the C drive. I've already downloaded them into the desktop. So let's go to C drive, RTO, and extract it here. And our course VM is ready. So now we can start with our course. One of the easiest and oldest techniques for persistence is a startup folder as well as registry run keys. These two techniques have been used by many threat actors, threat groups, operating in the wild. But I would say that almost every penetration tester and red teamer use these techniques during their operations. The reason is that these techniques are so popular is that you don't have to be running as local admin, so you can do this in medium integrity level, and both techniques require like really simple operation, meaning for the registry key, registry hive, you just change a specific registry key, and for the startup folder, you either upload your implant binary you want to run after a reboot or relogon of the user to a specific folder, or you implant a LNK file or link file to your binary. So let's do that. So let's go to, first let's focus on startup folder. So we go to user specific folder, which is C users, the username, and then we go to app data, roaming, Microsoft, Windows, startup menu, programs, and startup. So it's a long path. Now, if we open our implant is already in place, right? So we're gonna use this simple implant. So to set this persistence, we have to only copy our implant to the folder, or you can place, if you have, you can place an link file to your binary in the startup folder instead of copying the whole binary. But it's up to you. We are just going to use that, just copying the whole binary. So, and that's it. It's like we've copied the binary and now the persistence is ready. So to verify if it works, we have to either reboot the system or just relog in, and we will do this in a minute. But let's go to registry, reg edit, and take a look at the second technique, which is registry run keys. So we go to here, and currently it's empty, but we will set up the new persistence there. There is also run once sub key, which basically it does what it means, which is in a next reboot or a next relogin, it will run the specific program only once. Okay. So let's set up registry persistence. So we copy, and now it's here. To give you the full picture, there is also another key, which is also called a registry run key, which is machine specific. But to set this, these keys, you have to be running in a high integrity level. But for our exercise, we'll just stick with the current user registry hive. So now let's relog on and see if two Notepad programs will pop up. So we go to sign out. And relog in again. So let's wait for a bit. So we have one Notepad popped up and the second one is here. So let's try to figure out which are which. So this implant is running from command line, and current directory is here. So let's see the second one. So this one actually, we know that this one was launched from the startup folder, and this one was launched from Registry. So this is how, yeah, it's really super easy to set this kind of persistence. Before we jump into the next topic, let's remove this persistence both, so we get access is denied, which is obvious because our implants are still running. So let's remove it, and also remove the registry key, and we can actually verify if it's gone or not. Yep. So now we are clean, and we can go to the next technique. When the user logs into the system, there is a process called USERINIT, which does a couple of things for the user, and one of them is launching the Logon Scripts. And this is exactly one of the functionalities you can use for your persistence. So let me show you how it works. To set this persistence, there's only one thing you have to do, which is to set up one of the values in the registry. So let me start up the registry editor. So if you go to H key, current user, and environment key, there are a couple of things that are set up for the user, and if you add additional value to this key, you will tell the USERINIT process to use that value and start the logon process. The value name is USERINIT MPR logon script. So let me show you how you can set it up from the command line. So running this command, we set up in current user environment key, we set up USERINIT MPR logon script, and the value is set to this path. So in other words, we are telling the USERINIT process to start a logon.bat batch file when the user logs in. Okay, and let's go to our course materials to see what this logon batch contains. And this is really simple, right? It will launch our implant. So let's run it and refresh, and now the value is set. So now if the user logs out and logs in again, hopefully we get our implant running. So Notepad has run. So let's try to investigate what actually happened here. So we have our Notepad here, which was executed by the implant and which was running under CMD. So it's a batch file, and for a fraction of a second you might have noticed that there was a USERINIT.exe process, which was actually the parent process to our CMD. So
yep, that's how you can run, how you can set up your persistence with that function. And again, let's clean up the registry before we move on. Another popular technique used by many threat actors is shortcut modification. So usually the end user uses some form of link files or shortcuts to their either documents or programs they are frequently used. So in our, for example, in our course VM, you can see many shortcuts on a desktop, but also the programs pinned to the taskbar are also shortcuts, all right? If you want to modify a shortcut, it's pretty straightforward. You just right-click on an icon and choose properties, so you can modify the target, path, working directory, how the program runs. You change the icon, etc. Right? But in reality, you don't have that kind of access, right? So you can't just log into the target machine and right-click on some icon and start to modify that. Let me show you how actually what are these files. So let's go to our home directory, which is home path, which is and we go to desktop, and if you list the contents, these files are actually special types of files. These are LNK files. So if you try to see the contents of them, they are actually not text files. So you cannot take this LNK file, edit it in some notepad, and you're good. You have to use something else. So for that, I wrote a simple VBS script, which takes the existing shortcut, modifies that in a way that it preserves the original functionality of the link or the shortcut, and it will actually run our implant as well, right? So let me show you the script. We go to C drive, RTO, persistence, and take a look at that. So what this script does, it takes a putty.exe LNK file from the desktop, and it modifies it in a way that it will change the target path, but the rest of the settings will be the same, all right? And to do that, it will create another VBS file here, a putty.vbs, which will contain two lines. One is the first, it will run our implant, okay? And then it will launch the original program from the shortcut file. So in this case, it will be putty, and then it will save that in the file. So let me show you how it works. So first, let's create a copy. Let's call it original or origin, right? And so let's go to RTO persistence 01 user, and let's run the script. It's make VBS, right? So now if you take a look at here and compare it with the original, so now we are running a VBS script, okay, instead of a putty.exe. And the second one, the second difference is that it will be running minimize, not as a normal window. So let's first check if it works. So as you can see, Notepad has popped up and the PuTTY is also running. So let's see who actually, or what actually started this PuTTY, this notepad.exe. So notepad, as you can see, has been started, is a child process to implant, and implant was actually our program called by the VBS script, which is here. Excuse me. And it contains those 3 lines I talked about. So it's implanting, it's running our implant, and then it starts the PuTTY. So that's a simple way to how you can modify existing Alenka files. In 2017, ESET has released a report about one of the campaigns of the Turla group, and they described a backdoor which was using a backdoor called Gazer, and it was using an interesting persistent method, which was actually about changing the default screensaver on the Windows machine. So let's do the same thing. Let's first go into Regedit, because this technique is about changing a few keys in Registry. So if you go to current user and to control panel and desktop, this key holds many values which also configure the screensaver. Now we don't see anything specific for the screensaver apart from this save active setting. So it means that this machine is actually not using a screensaver. In reality, it probably might not be the case, but either way, let's configure that for our persistence. So let's run a CMD. And again, this technique works as only for the regular user. I mean, not only for, but you don't have to have high privileges to set it up. So what we do, we actually just create a value screen save.exe in this key pointing to our implant. Okay. And the second thing which is worth to said is also the timeout. So when the after what time the screensaver should be launched. Okay. So I set it for the 60 seconds, but let's set it for 10 just for the demo purposes. And that's it. Like this technique is done. We have set our persistence. So let's suppose that the user logged out. So sign out. And now relog in. And I'm not touching anything, so let's wait a few seconds to screensaver startup, and here we have it. So the notepad has been launched as a screensaver. And yep, that's pretty much it about this technique. You have to keep in mind that, so first let's get rid of that setting so that we don't get the screensaver popping up every 10 seconds. Okay. You have to keep in mind that in corporate networks, this screensaver can be set by the group policy, so from the Active Directory. And
In these cases, this technique might be unreliable, or you have to find another, like a bypass to another way to bypass that group policy setting. But yeah, that was how to persist using a screensaver. Another interesting technique is to abuse the PowerShell profile. And I have to admit that this technique would not work on every Windows machine. It's configuration specific, I would say. And the reason is that we are going to hijack the environment setting when the PowerShell is started. So this technique actually relies on, that something is running PowerShell on the machine, which is not like something which happens by default. But there are some cases where, for example, in corporate networks, that something is being run like some kind of script, for example, Logon script, which does something at the user's logon, and for that it uses PowerShell. So in these cases, you might use that PowerShell profile persistence technique. And this is how it works. Basically, when the PowerShell is being started, it uses special settings, configuration settings, environment settings, which are held in so-called profiles. And profiles can be set per user or per machine. And for the users, you have to create a profile.ps1 file in a specific folder. And this folder, so let me show you where it lives. If you go to home path, documents, as far as I remember, documents, and Windows PowerShell. Yep. In this folder, if you create a file called profile.ps1, it will be launched every time the PowerShell process is run under the specific user. All right. So let's do that. Let's create a simple profile PS, which will contain only one line, launching our implant. And that's actually it. Okay. So when the user or some other mechanism runs PowerShell, it will go to and check if the profile.ps1 exists, and if so, it will run it in the context of the user. And to verify, we can see the exact hierarchy between. So the PowerShell was run, and then it launched. It actually checked the profile.ps1 file, which launched our implant, which at the end launched our notepad. All right. So that is how it works. So again, as always, it's good to remove that persistence before we go to the next technique. Before we jump to DLL hijacking and DLL proxying, let's first discuss how dynamic libraries are loaded into a process. So when a new process is started, System Loader loads a main module of an application as well as NTDL library into the address space. Then it checks if there are any additional libraries needed by the program, and if so, they will get loaded as well. Okay, so that's basically how it works.
Now you might wonder how loader knows where to look for these DLLs, right? So in Windows, there is a defined DLL search order, and when a specific library is needed, system will look through all the places, one by one, until it finds the right module and load it into a requesting process. So for desktop apps, the order is following. First, look if the module is already in the address space of the process. Then check known DLLs by reviewing list of values in registry key. Then check the application folder. Then check system folders like Windows System 32 for 64-bit processes and Windows Syswell 64 for 32-bit apps. Then Windows System and Windows folders. And finally, check current directory and all the folders from a path environment variable. So that's the search flow. So in other words, when an application starts, it will check its application folder for the needed modules, but usually they won't be found there, and they are located in system folder instead, like Windows System 32. If you have a write capability into application folder, so you can write files there, you can also hijack the DLL search flow, and your DLL will get loaded into the process before the legitimate module, okay? Sometimes applications might try to load a library which is not present on disk, and in these cases, you can also hijack the search order flow if you have a write privilege in any of those folders. That's how some of the privilege escalation attacks work, though those which are based on DLL hijacking. When you hijack an existing DLL and your module does not provide the needed functionality, this might break the application, which is something you would probably want to avoid from OPSEC's perspective, right? So what you might do instead is to create a proxy module, okay? So when the application calls for a specific function your module does not implement, it can forward the call to a legitimate DLL to serve the requested function. That way, you can still get the hijack working without breaking the application, okay? So let's go to our course VM to see how it can be done in practice. One of the first things you have to do is to find a good candidate for your DLL hijacking, okay? So as for the persistence, you have to have two things. One, something which is running at some point, either automatically or really triggered by something. So it has to be something triggered by, for example, by task scheduler or some run key or something like that. And the second thing is that application has to be prone to DLL hijacking, okay? You might remember from the previous video that we have investigated registry keys for run keys, right? So let me show you again the contents, and here you can see that there are three applications started at the user logon, and one of them is bginfo, which is the application from sysinternals, which sets up the desktop, you know how it looks like, the background, etc. So let's see if we can write to the bginfo folder. So bginfo, and from the output you can see that the authenticated users can modify the folder. So let me check it out if it's actually if it's true. So we do a really simple test, and it looks like it succeeded. Now I need to make a note here. So you, like in reality, when you are on engagement, at this point you would copy out the whole, the whole application, so the whole folder into your test environment somewhere outside the target machine, and perform all the tests and development there. Okay, you wouldn't do that on your on the target machine on a live system, right? It's something obvious, but I wanted to, and I like highlight it here, that it's something important. Okay, so how we test if the BG info is prone to DLL hijacking. So for that, we will use one tool, also from sysinternals. And this tool is called Procmon, which allows you to monitor what is going on in the background in the system. Procmon. And specifically, when you are targeting DLL hijacking, you would actually be setting two filters. So one filter is that the result, so the result column contains not found string, okay? And the second one is actually, we are targeting another process, which is BG info. So with these two filters, you can see if there are any not found DLLs when the BG info starts. Okay, so let's start it. Let us also start a process hacker. And let's start BG info. So we go to C drive, BG info, and we start it. Now we see something happening here in the background. The application has started, so let's suspend it because it quits really quickly. And let's see the output from process monitor. So we see a lot of DLLs which hasn't been found, right? Like WinSock, version, SNMP API, etc. But it doesn't mean, so let's take a look at the process itself. So we go to modules, and we see that these DLLs are here. So WinSock is here, version is here, SNMP API is here. So why is that? The reason is, let's stop that. The reason is that these DLLs have been found in other folder. So here you can see it, the system loader didn't find that in the application folder, but if you turn off this filter, you will see that actually the WinSock DLL has been found in syswow64 folder, okay? And this actually means that the BG info is a 32-bit application. We can verify that here. It's a 32-bit application, okay? So at this point, we have several candidate DLL candidates for hijacking, right? We have the application which is prone to DLL hijacking. We have the right capability to into the folder, application folder, and now we have a list of application DLLs which can be hijacked. Now, which DLL actually choose? So what I usually do is I run a dump bin tool from Microsoft Visual Studio, which allows me to see all the imported DLLs by specific application. So in our case, it's a bginfo.exe. And now you see a lot of functions and a lot of DLLs which are needed by the bginfo application. So shell32, from that DLL, those functions are used. Only 32 are these, etc., etc. So what I'm looking for a DLL which bginfo uses only a small portion of functions. So winspool.drv has 3, only ACC has 3. Let me see if we can find a shorter list. No. SNMP API 3. Here we have 2, and only 1. But let me just for the exercise, let's focus on the one with the winspool.drv on those 3. Okay. So now what we need to develop a DLL which will act as a proxy between the application bginfo and the winspool.drv. So let's go to our course materials, and let's open up this file. And it looks like really simple DLL. So we have our DLL main function, which is called when the library is loaded into the process. And in this specific moment, we call the go function, which actually implements our malicious activity, so to speak. So in our case, I'm just creating a new process, launching our implant.exe. You can in reality, you would start some shellcode here, or some implant or something like that. But basically, for this exercise, I'm just launching implant. So as you can see, this application is really simple, and it lacks only one thing, which is proxying those 3 function calls to the original winspool. So how you can implement that? Of course, you could try to do some fancy stuff like loading the winspool DLL into the DRV into the process, and then get proc address and trying to match those. It's too complicated. The easier way is to use a linker from Visual Studio and to tell it that the specific function is actually implemented in different module. Okay. So in other words, if bginfo calls openPrinter_a function from winspool.drv, okay, it will reach out to the address table and see that this function is actually implemented in WinSPL HLP. So it doesn't matter the name, what name you take here. What is the most important is it has to be a copy of the original DLL, okay? And this function is actually implemented in this call, and we also add the ordinal number from here. 8F is 143 in decimal. And ordinal is just a sort of index on the address in the address table. So we lack those two. So what we do here, we just copy this line 2 times. We take the close printer. So we paste it here, and for ordinal we have 1D. We can translate that in Python, print int 0x1D, and let's take the another number, 40. Okay, so 29 is here. 77 will be here, and the function name is here, so we take that here, save it. Let's go to pers01 DL hijack compile. Okay, no errors. So let's see if it works. Let's see the exports from our winspool.drv. Okay, so now we can see the export table from our DLL, that those 3 functions are actually forwarded to another module in into those functions. And the last thing we need to do, let's clear it out. We need to copy our proxy DLL to the bginfo folder, and we also have to copy the original winspool.drv from syswow64. Winspool to bginfo, but we have to call it like this one. Okay, DLL. So far so good. And so let's run. We can minimize that. We can unfreeze this bginfo and close that, and rerun bginfo again. And nothing happened. So let's investigate why it didn't work. So let's run it again. Let's suspend this application again and make sure that, so we have winspool has been loaded, the other DLL was not loaded, and we can make sure, yeah, this is actually the original one. Okay, and from that do we see? Nope. So let me see if it actually has been loaded. WinSock version, and yep. So it looks like it worked. It's some sense, but so bginfo found our hijacking DLL, but for some reason it didn't it didn't like it, and it took syswow 64-bit. So I did that mistake deliberately because I wanted to show you that sometimes you might encounter some problems. Okay, and the problem is that bginfo is a 32-bit application. Okay, but our DLL is actually 64-bit, and I know it from here that we are compiling, we are using 64-bit compiler, and you can actually check that with dumping tool, because it says it's 64-bit. So you cannot use 64-bit module in a 32-bit process. Okay, so we have to compile that DLL using 32-bit compiler. So let's get rid of that, close that, and now we go to Microsoft Visual Studio, and we launch x86 native tools command prompt. Okay, so we do the same thing. So we go to RTO pers01 DLL, compile it. Okay, now we can try to verify. Now it's 86, so we can copy that back again, and let's see if it works now. And now it works. So let me suspend it. So you can see that bginfo started our implant, which was actually launching our simple shellcode, Notepad shellcode. And if you go to modules, you will see that that our WinSpool DRV has been loaded. Okay, and the original module is also in memory of the process. Okay, now let me show you one more thing, because it seems like everything is like good, right? But if you try to play with a tool and you go to printing, we get an error like before you can perform blah 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 something. No, there are some errors. Okay, and the reason is that sometimes implementing only 3 functions, it's not enough, because even if the information from the dump bin, as you could see, that bginfo only uses 3 functions, right? But in reality, it can also use getProcAddress functions and dynamically resolve the functions from the hijacking DLL. And in that case, our DLL is like, it's not ready for that. Okay, so what you could do, you could actually exports Windows syswow 64 and Windows spool, and actually do the same thing with all those functions. So you need to do progma comment for all those functions. Okay, and I let you do that as an assignment in this course. One thing you might be not familiar with and you get problems is that sometimes some functions are exported without any name, and they are callable only with using ordinal numbers. So in that case, you need to use that syntax. So for the function name, you put anything here. I use no name equals not name of the module dot hash and the number of ordinal. So as you can see here, as an example, and we export it as ordinal number 100, and giving information to the linker that this specific function is only callable using ordinal without any name. Okay, so that's your so to speak homework. All right, guys, and the last thing we need to do, let's clean up this mess. So we go to just delete pginfo. Now if you run it, should be all good. Right. So that was DLL Proxying. Component Object Model. COM is a platform-independent, distributed, object-oriented system for creating binary software that can interact with each other. Okay, so what does it mean? In plain words, COM is a dedicated system for developers to create libraries which can cooperate with other applications developed in different languages. So in other words, one developer can create a DLL which was written in, let's say, C++, okay? And that DLL can then be used by a C# application, right? We say that COM is language agnostic because it provides an ABI, application binary interface. So it makes sure that the apps are compatible on binary level. COM is really complicated system, but it's also very powerful, and a lot of Windows components run as COM objects or COM servers. So think about COM as a DLL, okay? Or to be more specific, COM objects are implemented as dynamic libraries in most cases. They can also be plain exe files, but mostly we use COMs as DLLs. Now, COM objects are identified by unique IDs. So when the application needs some COM, it will reference it by the GUID. Okay. What is most interesting, COM objects can live on the remote machine, and the application will never know that, about that fact. So the app will just call a function from a COM object, and this call will be actually serviced on the computer, which can be like on the other side of the Atlantic. But to the app, it will look like a regular local function call. Okay, it's totally transparent to the application. So let me show you how an application loads a COM object. So we have an app, okay, and this app actually uses some functionality which is implemented as COM. So it will call either co-create instance or co-get class object function, okay, and with a specific GUID. And these functions are actually implemented in OLE32 library. Then OLE passes this request to the local service control manager, or SCM, and saying like, hey SCM, we need that COM object, okay, with that GUID, right? SCM will take that information and start querying local registry, specifically HKey classes root hive, which is actually composed with the two hives. It is information taken from the current user hive and from local machine hive. So first,
it queries if the specific COM with a specific class ID or GUID exists in current user Hive, like software classes, okay, key. And if it's not, then it will query local machine software classes, okay. If it's found, then it will take the information from the Hive, from the key, and because it's usually it's a path, and it's a path to the DLL, so it will take that DLL and it will be loaded into the application, okay? And at that point, application now can call functions from that DLL. That's pretty much how it works. So that's what we call in-process loading, comma loading. Now, in that process, we can hijack one step, which is checking when the SCM checks the information from the registry Hive. And the reason is that the information from current user Hive is actually editable by the regular user. So you can change the information in these keys as a regular user. You don't have to be a local admin, okay? When you do that, the process goes pretty much the same. Like application calls OLI32, it will call, OLI will go to SCM, SCM will start querying registry Hive, but like when it goes to current user Hive, it will find in the information implemented by us, okay? And in that case, it will not check the local add machine software classes keys. And if it happens, then our malicious DLL will get loaded into the application instead of the benign original DLL. That's how the hijacking works. I also told you that COM objects can also be implemented as regular exe files. So in that case, we call it a local server loading. And the process is really pretty much the same. The SCM will query the Hive, and from the registry, it will find out that the COM object is a exe file. So we tag that exe file and start a new process, and the COM object will actually live in that process and will be available to the application via RPC. So application, whenever it calls the COM object function, it will be passed through COM local proxy in the application process using RPC to the actually COM server living in a separate process. Okay, so that's local server loading. And finally, I told you that the COM objects can also be reachable on the remote machine. So the process is different in a way that the local service control manager will call the remote machine SCM, requesting the specific server the application needs. Okay, so the remote SCM will go to its local registry Hive, and when it finds the COM server, either it's an exe file or DLL, it will create like a normal process, and the COM object will live in that process, and our application on our local machine will reach out to that remote process using RPC. Okay, so that's remote server loading. So now let's go to our VM and let's do COM hijacking. So first, let's take a look at where the where the information about COM object lives. Okay, so let's go to registry editor. So as I told you, HKey classes root contains a lot of information, but one of the keys is CLS ID or class ID. Okay, and it holds a lot of keys,
And if you take one of them as an example, so this one is called CLSID record info, all right? And if you go to incproc server 32 key, you will see there is a path to a DLL, okay? So in other words, it means that when some application calls that CLSID or GUID, in other words, that's that number, SCM will go to hclasses root and to that key, and it will search for that information, okay, and here, and it will find that this specific COM server is implemented as this DLL, and it will load that DLL into the requesting process. Now let's go back to, and I also told you that classes root, HKey classes root is composed of two hives. So information comes from current user and local machine. So if you go to current user, software, and classes, and CLSID, then here you can find a very short list of GUIDs, right? So as an example, this one is for the OneDrive, and it's in proc server, which is running as in process or a DLL. In this case, we have a local server instead of in proc server, and this actually server is at exe, not a DLL, right? So let's take a look at the last one, which was machine, local machine, and it's in the same, location. So CLSID, and local machine actually holds almost all the information about COM objects in Windows. So you can see it's a lot of COM objects here. So if you go up and open the first one, so this one is CLSID record info and the very same DLL. So basically, if an application calls for that GUID, SCM will actually load the information from the local machine registry hive. So that's where the information about COM objects lives in registry. Now let's do COM hijacking. So how to find a COM object which can be hijackable? So this case is similar to a DLL hijacking. You have to find something which is triggered either at the boot time or at the user logon time. Now a good candidate can be found in Task Scheduler. So let's take a look at that. So let's extract all the information about tasks. So we query the scheduled task, task scheduler, and take all the tasks into the XML in the XML format into the file. Okay, so let's go there and see how it looks like. The user, and let's take a look at that. So it's a very long list of tasks. So what we're looking for, we are looking for two things. In exec section, there should be something called COM handler instead of like a path to a binary, okay? And in a triggers, we're looking for a logon trigger because we want to have persistence, right? So let me scroll up. Yeah, we have a command here. it's another command, exec, and here we have it. We have a com handler, okay, which points to a specific class ID. So this is a identifier of the some kind of com object. And logon trigger is used as a trigger with a delay 30 minutes. Okay, so let me scroll up a little bit and see. Yeah, we have another com handler, and this time it's a logon. It's a delay for 5 minutes. So let's take this example. It's a work folders logon synchronization. Okay, so what to do next? The next thing is, let's take a look at how it looks in how this com object looks in registry. So we just query its classes root, like CLS ID, and we need this ID. So it's in proc server 32, and this com object is implemented in this DLL. Okay, so let's see actually where this thing is. Where does it sit? So is it current user or local machine? So we go to software, and it was classes. So nothing found. What about local machine? And it's in local machine. So now we know that this key lives in local machine. So if we put something in current user, we will hijack that com object. So let's export that key, export the whole key into RTO persistence 01. Let's call it task orig, like original, and let's get it from 64-bit. Okay, so now we have this thing here, right? Okay. So now let's take a look at hijacking com program. So I already prepared a template for that, and it's really simple. As again, a DLL main is pretty straightforward. Now, if you take a look at the com objects, the component object model defines that every com object has to at least export one function, which is DLL get class object, and this function is being called by the SCM. By the application. Okay. So what we do here is we implement that function, which is then exported, and this function will just call our implant and return OK. And that's it. Okay, so let's compile it. Let's go to pers 01 com and compile it. And it created a file called wrk folders shell.dll. And if you remember from the original, it was work folders. Okay, so we changed that a little bit. If you take a look at the compile bot, it's deliberately done in that way, and you will see in a minute why. So now our DLL is ready. The next thing we have to do is to implant it in Registry. So how we do it? We change this original exported key to current user. Okay. Copy, paste it here, and we have to change that path to point it to our hijacking DLL, and just make sure it's double backslash, and it's WRK folders. So let's save it as just DSK. And now we can import that. So we put import DSK to 64-bit registry. Okay. And let us check if this is actually okay. So classes root points to our DLL, and we can make sure it's in classes in current user. All right. So now we're set. Our persistence is configured. So in reality, now we would need to wait for the user to relog in or reboot the machine and log in back. But we can simulate that behavior, but just starting task scheduler. So we go to Microsoft, Windows, and work folders. So it was Logon synchronization task, and as you can see here, it's a logon, and it's triggered after 5 minutes, delayed by 5 minutes. So that is why we won't relog in. We just run the task here, and as you can see, our notepad has popped up. So let's check where is it coming from. So it comes from notepad and implant.exe. So it looks like our persistence worked. So let me close all of that. And move to the next topic. So previously, what we have seen is that we successfully hijacked the COM object, but we actually probably broke something, because we have hijacked the COM object without actually delivering the functionality the application needs. Okay, so what we want to do now is to fix that and actually make this task working as it's supposed to work. So to do that, let's go back to our source code and let's comment that out. And if you scroll down, I've prepared another version of our DLL get class object, which now does something additional. So we still launch our implant, but after that we load the original COM object, COM server, and we get process address of the original DLL get class object function, and then we call that function. So in other words, our COM hijacking DLL acts as a proxy, the very similar way as in the DLL example, but this time the only thing we need to do is to proxy this function, and the COM model will handle everything else, because when the application calls DLL get class object, the COM object will deliver more information about available interfaces this COM object implements, and application will be able to get to that these functions and interfaces using that information. So we are not even involved in that process at all. The only thing we need to be sure of is that the application will get the original DLL get class object function to run. So let's compile that again. And actually, let me add something else here. Let me add some sleep time so we could see that both DLLs, like the original COM object and our hijacking DLL, get loaded into the same process. So let's save it. Let's compile it again. Okay. And let's run the task again. So as we can see, Notepad has executed. So let's see where it lives. And now we see the parent process. So let's suspend that process. So task host w.exe is executing our task. As you can see here, task work folder logon trigger. Okay, so double click on it. Let's go to modules. And now you can see that both our hijacking DLL is loaded, as well as the original work folder's shell.dll. So that's how you can perform COM proxying instead of just hijacking the COM object. And as usual, let's clean up after ourselves. So we go to current user, software, classes, CLS ID, and we need to find, it was this one, 97. This is correct. So we delete that. We can actually release that process. We can close that. And let's run the task again to make sure that it runs correctly. So now our task, not our notepad didn't trigger, so we're clean. Scheduled tasks are also a very popular method for persistence among threat actors. So let's take a look at how we can use that for persistence. So there are two types of scheduled tasks that you can set. You can set them as the regular user without any local admin privileges, but they have very limited, functionality and what you can do with them. And the second type is setting the scheduled tasks as a local admin, and you can then run very powerful, and you have many configuration options at your hand. So let's take a look at how to set it up as a regular user. So first, we go to, so you just can create scheduled task and set it up to run at specific time of the day, and that's it. It's like, this is it. And now you can query if your target, my tasks go, and actually let's list and verbose, so you can see that the task name is my task go, it's interactive only, it's going to run this thing, and yep, to simulate you can run the task my tasks go, and yeah, it's running, right? So let me see how it looks on a process list. So yeah, our task has completed. So now the implant is running without parent process, and yep, and we are running as a regular user, right? So our token is not elevated, and we are in medium mandatory level. So that's how you can set task scheduler as a regular user. So let's remove that task as well. And let's go to more powerful position, which is running the same thing but as an admin. So you can create task as a logon at start time at specific times. So you can set various triggers here. To do that, you need to run elevated session. So we just run our command line as administrators, and let's go to our folder. And what we do, we create a new scheduled task, which is called Adobe Flash Sync, which will run at logon time, and the running task is actually our implant. Okay, so you can also verify that it's set correctly, and now we can relog in to the computer to see if it actually works. So we sign out, and logging back. So let's launch our process hacker. To see if something's happening. And Notepad has triggered. So let's see where it lives. It lives here. And again, our task has completed. So no parent process. So yep. One thing to note here is that even if we set the task as local admin, our task is running as regular user. As you can see here, the token is not elevated at all. So how to change that? So we can do that by modifying the task, and we need to do two things. Let's first go to. We need to first copy our task definition in XML format and save it somewhere. Okay, let's open up this file. And now what we need to do is in a principles section, we add something like run level highest available We save that. Now we need to, unfortunately, we need to delete the existing task. We cannot just reconfigure it with our new configuration. We need to remove that. Then we create the task again, and the configuration comes from the tsk.xml file. Okay. So now you can actually, let's query that to see if there is any changes. Can we see it here? Actually not. Probably if we query it here, it is going to run as local admin. So now let's relog on and see if it works as we want it. So we relog on. And now our implant should be running as with high privileges. So Notepad has fired. And as you can see, we are running as elevated with high mandatory integrity level, and we have a lot of privileges assigned to our token. And the same is with implant, right? So that's how you can create a scheduled task for your persistence and as a local admin, and preserve local admin privileges after user logon, or basically when your persistence fires. So again, let's remove that task before we move on to the next technique. All right. Another technique related to task scheduler is actually about modifying the existing task. So it's pretty much similar to what we did earlier, which is exporting XML, exporting the configuration of the task in an XML file, then modifying that XML, and then recreating a task with a new configuration. But this time we will do something different. So let's start again in elevated session, and let's query for the same task as we did during the COM hijacking. So I have prepared a command here. So as you can see here, we are targeting work folder's Logon synchronization task, which is run as a COM handler. Okay. So let's take, actually let's go to RTO pers, and now let's take that task and save it as tsk2 XML. Okay, and let's open up that task. And what we do this time, we will add additional action to the task. So what we do exec and here we get command and path to our implant goes here, implant.exe. Okay, so let's save it as task, let's say 3. All right. Now we need to delete this task. So we do just delete and force it. Delete. Okay. And now we create task again. Based on XML using task 3. Okay. And now if you query that, you will see the task to run is multiple actions. Previously it was ComHandler. Now it's multiple actions. So if we run that task, it will fire the both ComHandler, which was a com object or com server, and additionally it will run our implant as a next action on the action list. So let's do that. And let's use task scheduler again, because this particular task is fired with a 5-minute delay after the logon. So to simulate that, and actually let me see how it looks like here. So actions, it's a custom handler and start a program. Okay. So if we run it, our implant got executed. And you can verify it here. Yep, so Notepad was launched by our implant. Now, of course, in that task, you can also add adding another section we did earlier, which is run level and setting the highest available privileges for that particular task, so your implant will also run as local admin. So that's how you can modify existing tasks and make them like with multiple actions configured. So let's clean up after ourselves. So we delete the task again, and we recreate that from our original task. So now it should look okay. So let's go to another technique. Another simple but very powerful technique, persistence technique, is using Windows services. So you can either create a new service, or you can modify existing service if you can, and if you want to do that, you know, in a like a covert way. So how to create a new service? It's really simple. You can use SC command line tool, But for that, you have to have local admin privileges, and your session has to be running in elevated session. So what we can do is we just create a new service, and we call it, I don't know, update service. Then we give it a parameter, bin path equals, and blank space. It's very important. Now we give the path to our binary implant, let's say implant.exe, and we set it to start auto. Okay, and our service is set. We can check that. So before we start that, let me start the process hacker, and let me see if it works or not. So we go to Services tab, and we search for update service. Okay, it's here. You can see it will be running as local system, and by default, when you create a new service, it will be running as a local system. So highest the highest possible privileges on Windows. So, but here's one catch, and you will see this in a minute. So let's start that. So we simulate that the user has logged in, rebooted the machine. Service. Now we can see that it seems like it's hanging, and SC is running, but we can't see. Yeah, actually implant is running right here as a local system, but implant.exe is not actually a service. If you want to run as a Windows service, your binary has to be compiled in a special way, and it actually has to implement specific functions that Windows service has to have. And as you can see here, service start service failed because our implant.exe doesn't implement that. So I have prepared another template, implant template for services, and so you can find it here. So it contains a lot of much more code. All these functions actually are needed to make this binary as a service, so you don't have to be worried about that code. The only thing which is interesting from your perspective is this function runme, which is called here when the service starts. And what I'm doing here is just I get 30 second sleep, but I've also left here standard code for running payload, encrypted payload, AES encrypted. So here you have the function AES decrypt function, and you can put these like key here and your encrypted payload, and as well here here is the EAS Python script which will produce the appropriate encrypted payload. Okay, but for our demonstration we're gonna be using just sleep time, and that's it. So let's compile that. So compile SRV. Okay, now let's delete update service and change that to SRV, if I remember correctly. Now these pop-ups are only showing when you are running Process Hacker. So yeah. And now when we start, so let's start our update service. Start expanding. So you see the reaction is completely different. If we go to services, now update service is running, okay, with a process ID 4144. So we go to process, put this process, and our implant.exe is running here, okay. So, and it's running as system again. So yeah, that's basically how you can set your persistence as a Windows service. And also, if you want to, you know, you don't want to create a new service, but modify the existing one, you can do that as well with SC tool. So what you do, you just use scconfig. Let's use our service. Let's change the path to something else, like system Windows, system 32. Let's run notepad.exe. Okay, we have to stop first our service. Of course, as on the first example, this will not work. I mean, the notepad will start. We need to terminate that because that's the left off from the other from the previous example. But this service will like the notepad will run, but yeah, as we already know, notepad is not a service. But again, what I wanted to show you here is that you can configure the existing service without creating one. So now we start it again, and it eventually will fail. So our notepad is running here as system, but after some time the service control manager will give up and it will actually terminate that process. So let's wait a second, and as you can see, the notepad is gone. So usually I'm using the service template for persistence as a service, as I don't want to make it look like you know, generating any errors or some event logs that some service was trying to start, but it was actually crashing. So it's better to use something you know, more stable. So again, let's remove our update service, and that's it. So yep, that's how you can set up persistence using Windows services. So now let's talk about image file execution options. So image file execution options provide you with a sort of mechanism to make debugging an executable much easier. This is extremely useful if you have some problems with your code, and especially with a program's startup code, and specifically if you are trying to debug services. Okay, so Microsoft provided that kind of option built into Windows. Now, from our perspective, this Windows debugging feature can be used for persistence. Okay, and there are three interesting options we will cover in this video. The first one is Debugger, the second one is SilentProcessExit, and the third one is Verifier DLLs. So the Debugger option allows you to start your application you are investigating under the control of the debugger, like by default, okay? The second option, which is SilentProcessExit, does something opposite, which is allows you to monitor the what is happening at the end of the process, like when the process exits, okay? And the third option, Verifier DLLs, is related to Application Verifier, which is pretty old tool created by Microsoft. It was some sort of verification tool for testing applications for compatibility with Windows XP. So it's, I don't know, it's 15 years old or even more. But what is interesting in Verifier DLLs and Application Verifier is that it allows you to hook specific functions from a specified DLLs. Okay, so you can create a Verifier DLL and it will get injected into your process of your interest, and actually you can hook specific functions with that. But we will cover that later. Now let's take a look at where these all settings live. So as usual, settings for image file execution options live in Registry. So we go to Software, Microsoft, Windows, NT, current version, and we scroll down to image file execution options. So under that key, if you want to specify some options for the specific application, you just create a subkey with the name of your binary, and in that key you can set all debugging options you need. So let's do that for the debugger, okay? And we will be targeting BG info again, which is a 32-bit process. So we have to take into account that fact. So let's start. Actually, let's start. Let's start it with 32-bit command line. And we will need elevated shell as well. So let's go to RTO persistence. So for the first option, if we want to use a debugger option for our persistence, you just need to create one value in the registry. So let me copy this. So what we are doing is under that key, image file execution options, we create subkey of the name of our target binary, okay? And the value is debugger, which will hold a path to our implant. Okay, and I'm specifying that it's going to go to registry responsible for 32-bit applications or processes. If you want to do it for the 64-bit, you will set it up like that. But as we are targeting BG info, which is 32-bit app, we need to use this setting, and we can actually verify if it all looks good. So query okay, and that's it actually. So let's simulate how it works, let's first start Process Hacker, as we want to see what is happening. And let's open up BGInfo. And as you can see, Notepad has started. So, and you don't see the BGInfo started, right? And the reason is very simple, because this mechanism works like that. When the new process creation is requested, system loader will check if there is any setting for the debugger in this registry key, and if so, it will start that any application which is specified under debugger value, and it will actually pass the info about bginfo.exe as the input application for the debugger. So in other words, bginfo is started under the control of the debugger, which is in our case is implant, although we know that it's not a debugger, it's just our implant. But in normal usage, this value would point to a real debugger, okay? So like OLEDBG or Immunity Debugger, etc. Because our implant is not a debugger, then BGInfo is not started, okay? So you have to keep in mind that if you use that setting for persistence, you will need either to implement your implant as the debugger, or you just pick an application which is not like crucial or critical for the system, and it will get unnoticed if something breaks. So that was debugger option. Okay, so let's clean it up, because we don't want to leave any residue. The second option I told you about was SilentProcessExit, and setting this requires a little more effort. So as I told you, this works like the following. When the application starts, okay, and it's running, and after it has completed, it will call the exit process function call, okay? And if we have the setting for the silent process exit in our registry, then Windows operating system will launch our process monitor at the end. Okay, so let's set it up. So we need to set up three. Let me do this like that. So we have to set up again a BGInfo key with a global flag, value global flag set to 520 and 512. Okay, and again we are targeting 32-bit application, so keep in mind to set it for a registry, 32-bit registry. The second option we need to set up is another subkey under SilentProcessExit key, okay, with a value monitor process, which will point out to an application doing the monitoring. In our case, it's our implant. And finally, we have to enable that reporting mode set to 1. And again, that's it. So let's try to run BGInfo. So now it runs. Okay. Since BGInfo is has some timeout set, so after it exits, our implant has started. So To recap, this application is running at the end of the life of the specified process. Okay, and we are here. So let's clean up. So that was the second option for persistence. So let's clean up first before we move on to this third one. And a third option is called Verifier DLLs. So as I said, it's related to application verifier, which is really old tool. And it allows you to load your DLL, which is loaded at the process creation time to verify specific, whatever you need to verify at the process startup. And this option can also be used for persistence. So to set it up, it's really simple. You specify just one thing, verifier DLL, and with the name of the DLL. But there are two things you have to remember. So your verifier DLL or implant DLL has to be copied to the either system32 folder or syswall64 folder for the 32-bit applications. That's one thing. And the second thing is you need a special type of sort of DLL. It's not a regular DLL. And let me show you how this DLL looks like. So we go to admin and verifier. Okay. We have a verifier here. You can compile it. And let's open this up. So we go to audio, pers, admin, verifier, and let me walk you through the source code. So it's a DLL, so it holds the DLL main, okay. But there is an additional reason which of the DLL loading, which is DLL process verifier, and on that event we run process verifier function, which actually sets one specific structure in the memory of the process. And after that, we actually run our code as a thread. So our function go, which will launch our implant. Okay. And this is something you should be aware of, that you just cannot run go from directly. It has to be run as a separate thread, as this function should return as soon as possible. Okay. And so if you want to use that technique and use something different, then just edit this go function and you should be good to go. And the rest is pretty straightforward, since we need to have several structures, definitions, which then are used by the verifier. Okay, so that's the code. So we have compiled that. Now we need to copy vrf to Windows syswall64, as this is the application 32-bit application. Okay. And let me actually verify if the setting is done correctly. Query query. So we have that for, we are missing one setting. So we set the value for verified DLLs, but we also have to set global flag to 256, and now we should be good. Okay, so let's go to BG info and let's run it. So Notepad has started, BG info is running. Let's suspend it, and our verifier DLL is here. Okay, so it actually started our process, our implant, and so the way it works is that when the system loader creates a new process, it will verify this value, this verifier DLL values. Sorry, these values. Okay, and if it exists, it will load a verifier DLL into the process, which will then load all that DLL loads actually all the verifier DLLs into the process. Okay, so this is how it works. So yeah, that's the third way you can use image file execution options for persistence. So let me clean up. So the only thing we need to do is we need to remove that, and now hopefully BG info will run without any problems. Okay, so that was image file execution options as persistence. Okay, so application shimming, also known as Windows Application Compatibility Infrastructure, that was created by Microsoft for backward compatibility of software. As you know, operating system code base changes over time, and Microsoft tries to keep backward compatibility for many years, and they are actually pretty good at that. So application shimming was developed to help the software providers create some platform which will allow them to preserve the compatibility with a past software. So, for example, let's say that you have an application that was created for Windows XP, and using Shims, it will still work on Windows 10 without a need to rewrite the code. So it's really cool. App shims used to be very powerful. You could, for example, hook address table in the process. You could inject DLLs into the process. You can even patch the application code, like the running in the process on the fly with app shims. So it was really cool. Nowadays, most of these features or options were stripped off from app shims, especially if we talk about 64-bit applications. But there are still a few interesting options left for 32-bit options. So let's create a shim which will inject a DLL into a specific application. So we go to Application Compatibility Toolkit on a desktop, and let's go to 32-bit option, because, as I said, 64-bit is not that powerful. Let's run CMD here, and by default, not every option is enabled, but so we have to run it from command line with X option, and And we get, you know, a simple application which allows you to create a Shims. So let's try to create one. And since we are dealing with 32-bit Shims, so we have to target 32-bit application. And as we are talking about persistence, so we will target bginfo again. So let's create a new application fix. You can name it however you want. So let's call it just bginfo. Vendor is Microsoft. Now we have to point where the application lives. Okay, click next. We can skip this. We have the complete compatibility mode, so you can just pick specific compatibility mode, and you should be good. But we are actually interested in injecting a DLL, so we are selecting this. We need to set it parameters, and we have to point it to our DLL. And for that, we actually need to compile a new DLL. So let's go to Visual Studio and go to our RTO persistence implant, and there is a implant DLL.cpp. So let's compile that. Okay, so this is our path, and the name is implant.dll. So we can paste it here. Implant DLL. Okay, next we can set some additional things here, settings, but we just click finish. Now let's save it. Let's call it bginfo, and let's save it somewhere. Permissions, admin, bginfo sdb. Yes. And now we have to install it. You can do this from the command line. And to do that, we need admin privileges. So high integrity level session. So we go to RTO persistence 02. And we use a command line tool called sdb inst, and we give it a name of bginfo sdb. And that's it. So now if we run, let me start up Process Hacker. Now if we run bginfo or relogin, whatever, but we can just run it, it should actually start our, and let me quickly suspend the process. Oh, not that one. And let's go to modules. And here's our implant.dll running. And as from that process list, you can also figure it out, right? So that's really simple way to install a persistence. If you want to remove, so let me unfreeze that. If you want to remove your shim, you run the same thing, sdb with -u and the name of the shim database. Actually, it's actually here, so we need to -u, and the shim is gone. So now if you run pginfo again, it shouldn't produce any effect. All right, so that was application shimming and DLL injection. WMI, or Windows Management Instrumentation. So WMI is the infrastructure for management data and operations on Windows. It gives you an interface to the operating system that you can that can provide you some information and also event notifications. Okay. WMI is accessible by many scripting languages like VBScript or PowerShell, and it allows some sort of computer management, both local and remote. So WMI not only gives you some information about the operating system, so that you can query, okay, but you can also subscribe to specific events like network events, registry, file system events, or maybe you're interested in like CPU temperature, for example. Like all these events are accessible to you and you can subscribe to them. Most importantly, these event subscriptions will survive system reboot because they are stored in a dedicated cache or sort of database on disk. To create a WMI subscription, event subscription, you have to define three things. First is event filter. So you basically say or describe what kind of events you are interested in. Second is event consumer, which is basically an entity receiving the notification or like the consumer of that information. And the third thing is the binding between the two. So you bind the specific filter with the specific consumer, and the event subscription is ready at that point. So let's jump to our course VM and to define our WMI event subscription for persistence. So let's start with WMI event querying. So let's see what kind of event subscriptions are already there on the system by default. So to query and to set up WMI eventing, we need local admin. So first we query event filters. So that's the command. We will use WMI client, command line client. And we are querying this namespace for specifically event filter. Okay, so we have one event filter for SCM, event log filter. So SCM is Service Control Manager, and it's querying for some MSF, some MSFT logs. The second command for querying, we are doing the same thing, but we are now querying consumers, and our consumer is actually the Service Control Manager. Okay, and the binding, if you want to see the binding, we can query filter to consumer binding. And yeah, we get that. So what we can do, we can set up first. So we want to create a new event subscription. So we start with first, let me show you the whole definition. So we are creating a new filter. Okay, create a new filter with name inFilter, and we are specifying that we want an event of a process being in memory, wordpad.exe, for which is 32-bit. It is a Windows process. So create that. Then we define our consumer, which will be our implant, right? And finally, we create the binding between infilter and inConsumer, which was defined previously. So that's basically, we can actually check if it's on a list, and it is. So the last thing we need to run is a WordPad. So WordPad is running, and at some point our implant should fire up, and you can see it here. And it's actually not running in the background. It's not running in the desktop, so Notepad is not visible because WMI by default runs as anti-authority system in session 0, while our Explorer is running in session 1. Okay, session number 1. So that's why this is not visible. So keep in mind that if you are using WMI eventing, you will end up in by default you will end up in session 0 as running a system, and yeah, you have to pivot from this session to session 1 if you want to interact with users' processes. So that's how you can set up a WMI eventing. We can of course clean it up, but before we do that, let's discuss how it's actually can be used during your operation. So setting this filter for WordPad.exe doesn't make sense, right? Because you wouldn't expect that your target user will actually fire WordPad. But there are other applications, especially used in corporate environments. So for example, you can set up this event filter for Outlook.exe or some web browser as well. Okay, and that it's more like a productive, and you will be like sure that that kind of persistence will fire up at some point. So as usual, let's clean up. So to clean up, we need to we delete the binding, then we delete the filter, and finally we delete the consumer. So if you query, it's all gone. AppCert DLLs are a really interesting feature of Windows. So AppCert DLLs are loaded during the first call of any of the Win32 functions which are responsible for creating processes. And these are create process as a user, create process with logon, and create process with token. So if any one of these 4 functions are called, then special type of key is read from the registry, which is called AppCert DLLs, and any DLL listed in that key will get loaded into a newly created process. Okay, so let me first show you where it lives. So let's go to Registry Editor. and we can go to local machine, system, current control set, control, and session manager. And under session manager, if there is a subkey called AppCert DLLs, which contains values with paths to the DLLs, so all these DLLs will get loaded into a newly created processes. Okay. But those DLLs cannot be like any other DLL. It has to be properly written. So let's go to our course materials, 0 to admin, AppCert, and let's take a look at the source code. So this DLL has to have a create process notify function, which is actually exported. Okay. And because that function is being called when the create process or one of those calls, one of those functions gets called, then AppCert DLL key is read from the registry, and the path to the DLL is extracted, and this DLL is loaded into the process, new process, and this call is it gets called. Okay, so it has to be in our DLL. And what it actually does, it calls go function, okay, with the application name. So when the create process notify is called, and the first parameter of that function is actually the path to the process that this DLL will get injected into or loaded into. Okay. So I'm passing that path to a go function, and what I'm just doing here as an example code, I want to show you that you can actually filter, so to speak, specific processes you want to execute your shellcode in. So again, we go to our create process notify function gets called, okay? And then we do a comparison if this application is the same as what we are interested in. So the target is defined here as cmd.exe, and if it matches, then our go go function gets executed, which will actually print something on a debug view, just a simple string message. And if it's not the case, then it will return empty status back to the system. So this is like a simple way you can filter that you will run your code inside specific process and not on every process. So let's compile that. Actually, let's run that as an administrator, because we will have to set registry keys. So we go to RTO pers02 AppCert, and we run compile. Okay. So the next step we do is we set up, we need to set up the registry key. So as I said, we go to local machine, system, current control set, session manager, AppCert DLLs, and we create some value, like for example AppCert. You can specify other name. It's up to you, and it should contain the path to our DLL. Actually, it should be 6 DLL, right? And that should be it. So let's reboot the machine to make this new setting be applied, and let's see what happens next. So now we log on. So let's see how many processes has loaded our DLL into their address space. So to do that, let's just search for AppCert DLL. So for example, cmd explorer.exe, let's see the explorer. So we modules, and here's our AppCert DLL. Okay, Ruby, which is actually should be running as system as far as I remember. Oh, it's here. Is it? Yeah, it's running as system, and the module is also loaded here. Yep. So that's how you can inject your DLL into various processes. So let's start a debug view and see what happens when I run cmd. So as you can see, it gets, so our function, let me show you here, our function got called because that if statement was true, and that actually function got executed. So if you want to weaponize that, you will change that into some like decrypting your payload and injecting it somewhere or something like that. Okay. Keep in mind one thing, that if you this technique doesn't work reliably against GUI applications. So let's start Notepad, for example, and see if it gets injected, and it didn't. Okay, so for some reason AppCert DLLs does not get injected into the GUI applications. So for example, if you are targeting browser or Outlook.exe, that might not work. Okay. And finally, let's clean up. And it's obvious, it's because we need to be local admin. So we delete that, and now we need to reboot the machine. So that is how you can persist on the machine using AppCert DLLs. AppInit DLLs are pretty similar to AppCert DLLs. They are also loaded at new process creation, and the setting also lives in Registry. So let's go to Registry to see it. So we go to local machine, software, Microsoft, Windows, NT, current version, and we have to go to Windows. And there you can find AppInit DLLs value, which is empty right now. So to enable that, you have to do two things. You have to set this value with some path, okay, to your DLL. And you also should add additional value called load AppInit DLLs and set it to 1 to enable that feature. And what is interesting is that during the process creation time, it is that user32.dll library which actually checks if this key is not empty, and it will try to load those DLLs from that value. Okay, let me let me show you that. And for that we will use dumpbin tool again. So let's see imports of user32.dll, and let's find the string AppInit. And as you can see, it comes from it calls load AppInit DLLs, which is exported by this DLL, which is actually the virtual. It's a virtual library, which actually is in kernel 32. So if we go to kernel 32.dll, it is there. Okay, so it's like new process is created. If a user32.dll is loaded, it will check for this key and will call kernel 32 with this function, and eventually the library from the registry will get loaded into a new process. So we can use any almost any DLL for that. It's not like with AppCert DLL case where the DLL had to export specific function. You can actually use any valid DLL, and we could also use our implant DLL. But if you take a look at the source code, you will notice that actually, so we call, when the DLL is loaded, we call go function, which will create a new process and will create an implant, right? The problem with that is that with that kind of structure, we will end up with infinite, loop of creating new processes, because when when this gets called, an implant will be created. It will get this DLL loaded into itself, which will call implant.exe and so on and so on. So in this case, so in case of AppInit DLLs, but as well as with AppCert DLLs, you have to be very careful about how you use that functionality, because your DLLs will get loaded into many processes, and if you done something like implement your malicious code improperly, you will get you might just break the system. So let's change our function that it will just return 0, and we just comment this out. If you run some sort of shellcode here instead of creating process, that should be fine and pretty safe. But again, don't create any processes. All right? Okay. So let's go to RTO to compile, implant, and compile DLL. Okay, looks good. And now the only thing we have to do is to set up those two keys. So first we add a value to AppInit DLLs with a path to our DLL. And the second thing we need to create a new load init key value set to 1 to enable AppInit DLLs. Okay, so if we refresh, we have that enabled. And now if let's say I run process hacker, so our DLL should get loaded into process hacker, and it has actually got injected. Okay, if we run something new, it should be also the case. So implant.dll got injected. So that's one of the old, it's a really old feature of Windows app DLLs, AppInit DLLs, and currently, as far as I remember, Microsoft discourages of using that technique for like legitimate use. So let's clean up as usual. So we set AppInit DLL value to 0, and we can disable just setting AppInit DLL, load AppInit DLL's value to 0, and we should be good. Another persistence method is by using netsh helper DLLs. So netsh is a command line tool which allows you to display or modify the network configuration of a computer. Okay. Now Microsoft added some extensibility feature allowing developers to add a new sort of functionality to netsh, and that kind of feature is called netsh helper, and is implemented as a DLL. So for example, if you want to be able to configure DHCP servers on a local machine, there's a dedicated DLL that does DHCP configuration, and this DLL is called dhcpmon.dll, and it is a netsh helper. Okay. This feature can be used for persistence, but it has one downside, which is it actually relies on running netsh. So in other words, your victim machine has to use netsh during runtime to actually execute your helper DLL. It might be the case where, for example, domain admins or workstation admins run some scripts on the user's computer, and these scripts utilize netsh, and in that case your DLL gets executed. But if it's not, if you don't find a similar thing, you won't be able to use that, like this method for persistence, unless you set up something like simple batch, which will execute during logon time, for example, and it will call your netsh. So it would be like a two-level persistence method. Okay. So let's see how the netsh helper DLL looks like. So let's go to our course materials. We go to 02 admin, net help, and let's take a look at that. So it's basically a regular DLL, but it has to export a function called init helper DLL. Okay, and this function is called at load time. So when a netsh starts and it starts loading all helper DLLs, each DLL will, in each DLL this function will be called. Okay, and our implementation is really simple. It just creates a new thread running our Go function, and this is all something you are already familiar with. It will just execute our implant. So it's really super easy and super simple. So let's compile that. And I'm still running this as admin because I will need high privileges to register netsh helper DLL. Net helper. So we compile that. And registration is actually done in Registry Hive. but you can also use NetSH to add the helper, and the command is really simple. So you run NetSH, add helper, and the path to your NetSH helper. So we already registered and it already executed. Okay, let me show it again. Let's close that and let's run NetSH, and again our DLL gets executed. As you can see, so NetSH loaded our nethelp DLL. Okay, that's our DLL, which exports init help DLL, helpful DLL, and that got executed. It executed our implant, and finally our implant executes Notepad. So that's one of the techniques, another technique you can use for persistence. But again, it has some limitations. It's relatively dependent on the configuration of your victim machine, unless, as I said before, you can build something more complicated using your own batch. To clean up, we can use nethelper as again. This time we just delete. Oh, I have to get out. And this time, if we know we run a NetSH, it will not get executed. It won't execute our implant. So that was NetSH helper DLL persistence. Another technique quite popular among the threat actors is what I call Winlogon shell and USERINIT piggybacking. So let's take a look at Registry again, and let's take a look at the Winlogon configuration. It's actually interesting. So we go to System, Microsoft, Windows NT, current version, and we go to Winlogon. So we have a lot of values, configuration values for Winlogon, and we are interested in two of them. One is shell, which contains the system shell of the user, and it's set to explorer.exe. So it means that when the user logs in, this value gets read, and this process starts to be like a system shell of the user, okay, on user session. The second value, which is interesting from my perspective, is USERINIT, which is a process launched by Winlogon, and which initializes the whole user session. Okay, so the flow is like Winlogon starts the USERINIT, and USERINIT starts shell. So what we can do about it? We can actually those two values can store more than one program on one application. So let's first add one key for shell. So we need a high privileged session, and what we actually do, we will edit a shell value with explorer, comma, and implant.exe. So it means that USERINIT process will read that value, and it will start both explorer.exe and implant.exe. Of course, as you can see here, we cannot provide the whole path, so we need to copy our implant.exe into system32 folder. So let's do that. And now we should be good. So let's relog on. And see if it executes. So our notepad is already running, so it means that we successfully executed our implant, hopefully. And let's see if we can actually see what is happening. So here, as you can see, USERINIT is running explorer.exe, and at the same level as Explorer is our implant running. Okay, so it was a child of the USERINIT process. So that's one technique you can use, and the other one. So let's clean up first before we set up another technique. And now we are targeting, we are cleaning up, and now we are targeting USERINIT value, where we provide USERINIT as it was, and it will also so Winlogon will start USERINIT and our implant as well. And let's relog on again. So again, our notepad is running. So let's see. So now implant is at the same level as USERINIT, so is a child process to Winlogon. So it means that Winlogon started implant, not the USERINIT. Okay. So yeah, that's how you can use that technique for persistence as well. Let's clean up before we move on. So we need to get rid of, or actually revert, settings for the USERINIT value. So we set it up back to USERINIT alone. And let's delete implant.exe from system32. And that's it. We are clean. If a computer is a part of Active Directory domain, time synchronization between machines is crucial, right? Because Kerberos protocol relies on reliable time sources. Now Windows has a built-in time service. It's called W32Time, which is responsible for time synchronization. And it uses NTP, Network Time Protocol, to align computer clocks on the network. Now, Windows operating system provides support for a variety of hardware devices and network time protocols using the so-called time provider architecture. We have two types of time providers. It can be input time provider, which retrieves accurate timestamps from hardware or from the network. And there are also output time providers, which provide timestamps to other clients on the network. Now, time providers are managed by the time provider manager, which is responsible for loading, starting and stopping time providers, and it is controlled by a service control manager. So all this means that if you create a special DLL in a form of a time provider and register it on the machine, it will get loaded by the time provider manager at start time. Okay, so let's take a look at where the configuration lives in registry. So we start up the registry editor, and let's go to machine, system, current control set, services, W32 time, and time providers. And currently we have 3 time providers registered. So we have NTP client, which is enabled, NTP server, which is disabled, and vMIC time provider, which is the virtual machine time synchronization DLL. So it synchronizes the time between the machine and the guest machine and host machine. Okay. Now, so what we need to do, we just create a new subkey under time providers key, which has to have 3 values. The DLL name, which points to the DLL, enabled, it has to be set to 1, and define if it's input provider or not. Okay, that's basically how you can configure your time provider. And we also need to create a DLL, which is in our course material already created. So let's take a look at that. So when you create a DLL, time provider DLL, it has to provide 3 functions which have to be exported. Okay. So these functions are timeprof open, timeprof command, and timeprof close. All this is taken actually, the code is actually taken from Microsoft documentation. So like from your perspective, the only thing you have to know is that the time provider open is called when the time provider is loaded into the process. Okay, so what we do here is we launch our go function, which runs implant as a separate thread. Okay, and then it does provide some information back to the time control manager. So let's compile that. For that, we will need start up our command line, and let's go to RTO persistence 0 to admin time provider, and let's compile it. And now we have to create. So let's first see if our time service is running. It is stopped. Okay. Let's check what is its. So it's auto start. So what we need to do now is we have to create a dedicated time provider key in registry and start the service. So let's do that. So first we create a timeprov subkey under time providers, okay, with the value of DLL name pointing to our time provider DLL, and I'm pointing this at system32. But you can specify other path as well. So that's one. Then we have to create another value saying that this time provider is enabled. And we also need to specify if it's input provider or not. So we're we're doing with that. With this command, we're doing this. And the last thing we need to do is to copy our time provider DLL to Windows System 32. And if all goes well, so let's go to the, it's actually stopped. So let's start the machine, the service. And as you can see, our implant got executed. So let's take a look at that. So you can see our time provider DLL has been loaded. There are other two. So we make time provider.dll, which is visual machine integration component time sync provider library. And the other one is W32 time DLL, right? So refresh. So that's the NTP client running on that machine, and our time provider is here. So that's how you can use time providers for your persistence. Now let's clean up again. So we need to stop the time provider, time service. Then we need to remove Windows System 32 time provider DLL, and we delete the key containing our time provider definition or configuration. And now you can start time 32 back. And one comment here. So this persistence uses services, and services commonly run in session 0. So that is why our implant has also started in session 0. And actually our notepad is not visible to the user. Okay, so that's something you should keep in mind. Let's actually terminate that as well. And now we're clean. Story about port monitors is pretty much the same as with time provider libraries. Windows provides a printing functionality to the user, okay? And to make it more extendable, Windows allows you to install so-called port monitors. So port monitor is a DLL that passes raw device commands to the printer, either over the network or printer installed locally, like on a serial port, for example. Okay, and so port monitor is a sort of linking entity between spooling service in the system and the printer. That's basically it. So what we need to do is we need to create a dedicated port monitor DLL and configure the system to use it if we want to have a persistence, right? So let's take a look at the DLL source code. So we go to our course materials, pers 0 to admin port monit, and let's take a look at that. So port monitor DLL has to export one function, which is initialize print monitor 2, and that function gets called when the port monitor DLL gets loaded into the process. And it has to fill out a special function, structure, monitor structure, which holds pointers to various functions that port monitor should provide. Okay, and these functions are here. These functions are it's like a mandatory minimal list of the functions that have to be implemented. But as you can see, all the functions are doing nothing actually. They are just return some expected values, and that's it. So our initialize print monitor to function, what it does is actually it's going to launch our go function in a separate thread, and go function is already known. So far it will launch our implant. So if you want to use that for your persistence, you can change, you can provide enter your malicious code here. Okay, either it's a payload, something whatever you want. So now let's take a look at where this configuration goes. So we have to go to registry editor, and the configuration lives in current local machine, local machine, system, current control set, control, print, and monitors. So under that key, we will create a new subkey which will point to our DLL, and it's really straightforward. The only thing the only value it has to hold is a driver value, which will point to a name of the DLL, and you cannot provide the whole path to the DLL. It has to be copied into the system32 folder. Okay, so let's do that. Let's compile our port monitor DLL. So let's go to RTO, pers02, port monit. We compile it. Now we can copy port monit DLL to Windows System 32, and we have to add a value driver to under print monitors key with subkey port monitor. Okay, and this actually name is, it's up to you how you call that subkey. And with that, now the system persistence is set. So to make it run, the system has to reboot. Okay, so let me close all the things and restart our machine. So we're logging back, and while we are logging in, I can also tell you that there is another way to configure your port monitor. Microsoft introduced a dedicated API call, which is called add monitor. So if you call add monitor function with specific parameters, you can register your port monitor in the spooler service. Okay, that's the other way you can use that for setting up your persistence. So let's take a look at our process list and see if our persistence worked. Port monitor is all the port monitors are loaded into the spool into the spool service. So as you can see, our implant is running, and Let's go to modules, and our portmon DLL is loaded, right? And we are running as system user. So we successfully gained persistence using port monitor. So let me close that. And let's clean up. So one of the first things we have to do is to unload port monitor, which is not a safe thing to do, but we need to do that if we want to remove a DLL from the disk. So portmon, and we also need to remove the key. So that's it. Let's move on to the next technique. Local security authority. So LSA is a protected subsystem that authenticates and logs users onto the local system. It also maintains information about all aspects of local security, also known as local security policy. Now, LSA lives in LSA-as-a-Persistence process, and we all know LSA-as when we use Mimikatz to extract credentials material from that process, right? So it holds things like hashes, passwords, tickets, and other secrets used in Windows. But not too many people know that LSA-as can also be used for persistence. And it's particularly interesting persistence because when it fires, you end up in a high privileged context. Okay, so you run as system user, and your code runs inside the LSA-as process. So it means that you can easily take the credentials from the same address space. So how can we do it? There are at least three things you can do to use LSA-as as your host for persistence. You can build authentication package, security support provider, and LSA password filter. And all these three elements work as DLLs loaded by LSA into LSA-as process, okay? Authentication package and security support provider are very similar in their design. So auth package is mainly for handling user authentication, while SSP is a sort of implementation of security protocols like Kerberos or LAN manager. And more importantly, you can create a DLL which is authentication package and SSP at the same time. It only requires to export some different functions, but that's the only difference. Password filters are a sort of main mechanism of password enforcement in Windows OS. Now, one comment I have to make here is that this technique might not work if LSA-as is running as a protected process light. And so in this case, your DLL has to be signed by Microsoft. But by default, LSA-as isn't running as PPL, but nevertheless, you have to be aware about that limitation. Now, how LSA loads authentication packages and SSPs. So LSA automatically loads all registered security support providers and authentication packages into its process at bootstart. And in case of SSP, it calls SP LSA mode initialize function to obtain pointers to the functions implemented by each security package in that DLL. Okay. So those function pointers are passed to the LSA in an array which is called seg package function table structure. So on this example, you see that my SSP DLL provides two security packages, my security package 1 and my security package 2. Okay, and both these structures hold pointers to specific functions which have to be provided by the SSP DLL. In case of authentication package, LSA calls LSA app initialize package to provide, the authentication package a chance to initialize itself. Okay. So let's first cover auth packages and SSPs, and then we will handle password filters. So first, let's take a look at the source code of our SSP/authentication package. So let's go to our course materials. And let's take a look at that. So there is a lot of code here, but the main interesting, like the most important thing are two functions. So SP LSA mode initialize gets called by LSA if LSA interprets our DLL as SSP. Okay, and when this is called, then we run our go function, okay, as a separate thread, and we also initialize this structure of pointers, which is here, and this table or this structure is actually initialized here. So this structure contains, all the pointers that are needed for our security package or provider. Okay, and they are actually defined here. So as you can see, they hold almost no code. It is pretty similar to our port monitor DLL. We have few exceptions. So for example, get info provides some structure back to the LSA, but in most cases these functions are just returning 0. And if LSA tries to initialize that DLL as authentication package, then it will call this function, LSA AppInit initialize package. And we do the same thing here. So we create a thread running our go function, and then we continue with initialization. And our go function is pretty standard. So we run our implant. Okay, so that's our code. Now let's take a look at where is the configuration of LSA in registry. So we have to go to a local machine, system, current control set, control, and LSA. And there are two variables there. Authentication packages, okay, which is multi-string, and it is important, but you will see in a moment why it is important. And also security packages. So if you want to register your DLL as authentication package, you add your DLL name to that value. And if it should be a SSP, then you add your name of your DLL into this value, security packages. Okay, so let's do that. Let's first compile our code. So we go to RTO pers02 authentication package. We're gonna compile. Then we need to copy our SSP DLL to Windows System 32 directory. And then we need to add our security package to authentication package to the appropriate value in registry. So when you're dealing with multi-string types in registry, so you have to use 0 byte in between the strings. Okay, so when you run it and you hit refresh here, we get that list. Okay, and basically that's it. So our persistence is ready right now, so we can test it out by just rebooting our machine. So now let's relog on. And let's see if our implant is running. So we scroll down, and yep, our implant is running as anti-authority system. We can double click and check the modules loaded. So here is our DLL, okay, loaded, which fired up our implant, which launched our notepad. So that's first technique. And the second one, so registering as SSP, we can do that by using reg tool. So first let's remove our DLL from authentication packages value, and we can verify if it's actually holding true. MSV1 is the default authentication package for Windows, which handles, local user authentication. So now let's query security packages. So the list is empty, but it's still multi-string type. So we set up our SSP AP DLL, okay, and we're all set. So again, let's reboot the machine and see if it worked as well. So we relog on. And let's see if it works. So fingers crossed. And again, we have successfully persisted the reboot. This time using SSP functionality of LSA. So, yep, we can actually terminate that. So yeah, that's how you can use LSA authentication packages and security support providers to persist on the Windows machine. So now let's clean up before we move on to LSA password filters. So we need to set security packages back to the original. Let's double check. We don't want to mess it up. Looks good. And we have to remove Windows, our SSP AP DLL. And access is denied because the DLL is used by LSA-as, so we can unload it from live process, which is basically not a safe operation, but we are going to restart our machine before we do next exercise. So now we can remove that, and that's it. Let's move on to password filters. So LSA password filters. So filters are used to validate potential password changes against like password policies. Okay, so when a user changes his password, LSA requests validation from each registered filter. It passes through all of the filters until all of them validate a new password against password policy. And if not, then the password is rejected. But basically, that's the main function of the filters. Password filter has to export 3 functions to be successfully registered. So let's take a look at the source code. I have implemented very simple password filter, which basically does nothing except starting our implant. So as I said, it has to export 3 functions: initialize, change, notify, password change, notify, and password filter. So this function gets called when the password filter is loaded into LSA, and here we start our go function, which launches our implant. All right, and to the register, the registration is pretty similar to authentication packages and security packages. We need to change notification packages value in LSA key. All right, so that's basically pretty straightforward. So let's do that. Let's start a CMD, compile our code, and then register the DLL. So we go to 02 password filter. We run compile. We have our DLL here. So now we have to copy it. Pass filter DLL to Windows System 32. Okay, and then we need to, so that's the value of current value of notification packages, and it holds SCE as SLI, and again it's a multi string type. So to add our pass filter, we need to add this 0 between the strings, and yep, we are good to restart. So let's do that. So we log in. And LSA should already load our DLL into its address space. Let's check it out. and indeed it did. So pass filter should be on the list. Pass filter is here, right? It exports those 3 functions I've mentioned, and it successfully started our implant. So yep, that's how you can, that's a third method of using LSA for persistence. There are other methods available as well, but at this point I think you get pretty solid, couple of methods you could use during your engagements. So let's remove this persistence. Yes, we want to remove that, or actually change. Let's query that to make sure. All right, and we need to unload our pass filter to remove it from Windows System Pass Filter.